Alright, so let's pick up where we left off. We're going to move from series circuits to parallel circuits. I have an example parallel circuit where we have three resistors in parallel, and hopefully we recognize why they're in parallel besides the fact that they're parallel to each other. What do they mean? What does it mean to be in parallel? There are multiple loops from the positive to the negative terminal. So there's one loop, don't circle these yourself, two loops, three loops. Alright, so coming from the problems we did with Kirchhoff's laws, this is much simpler to look at and understand. Okay, so let's get right into circuit properties. There are three loops, and we know from the loop rule that for every loop, the drop across one, or all the resistors, has to equal the voltage source. So each loop only has one resistor. Okay, so the voltage across here must be the same as the voltage across there, which must be the same as the voltage across there, irrespective of the resistances, because each one only has one resistor. So this one must have a 12 volt drop, this one must have a 12 volt drop, this one must have a 12 volt drop. And again, the analogy is, think of this as a river system where we split up into three channels, 1, 2, 3, and in each channel has the same drop, like over a waterfall. Okay? So, in other words, our EMF equals V1 equals V2 equals V3. Okay, so there's the loop rule applied to a parallel. Very different in a series. In a series, they add to the EMF because there's only one pathway. So if I go to my chart here, the EMF is given as 12 volts, so we know each of the voltages is 12 volts as well. Okay, so what about current? Well, by the junction rule, if I've got a certain amount of current coming in, some of it's going to go here, and then the rest is going to go here, and then it's going to split off again, and the rest goes up there. So it's not too hard to figure out that our circuit current is nothing more than the sum of each branch. Whoops, that should say plus. And we'll see how that works out in a bit. Okay, and then what we have to do is come up with is a resistance equation. So let's go to our chart here and let's figure things out. Okay, so I know I have 12 volts across 4 ohms, so this must be by Ohm's law, 3 amps. I have 12 divided by 8 here, so that's 1.5 amps. Okay, and if this is 6, all right, so I can do a number of things. I can apply Ohm's law for R1, so 12 divided by 6 must be 2 ohms. So let's look at that for a second. So this is 2 ohms, 6 amps, this is 4 ohms, and we found that to be 3 amps. Okay, 3 amps here, and then we found the last one to be 1.5. So there's a number of things that we can infer from that. Why does this have 6 amps? Because it has the least amount of resistance for a given voltage. The voltage is the same, 12 volts for all of them, so there we see what we're used to, less resistance, more current. Let's see if the junction rule is followed. So, well, let's see, I've got 6 amps here, 3 amps here, 1.5 amps here, so they all come together right there. So I must have 6 plus 3 plus 1.5, 10.5 amps here, 10.5 amps right there. So 6 go to the right, then 3 go up that way, or excuse me, 4.5 go this way, then 3 branch that way, leaving 1.5 there. So right here I have 1.5, then I have 4.5 when they branch together, and then when it meets the 6, I've got 10.5. Okay, I know I've done that quickly, but you can work out why those numbers should be in the junction rule. So let's see if Ohm's law, let's see, so we add these all up, we see we have 10.5. Okay, now we can get the effective resistance of the circuit. We've got 12 volts across 10.5 amperes. So according to Ohm's law, we can divide the two to get the effective resistance. I forgot my calculator, so this is not necessarily an easy number. So we have 12 volts divided by 10.5, and we see that, excuse me, this is 1.14 ohms. Wait a second. There's no way that 2 plus 4 plus 8 add up to 1.5 or 1.14. So something different is going on here. Parallel circuits, you cannot simply add the resistors to get the effective resistance. That's series circuits. Something else is going on here. I will do the derivation in class, and it's not immediately obvious how we would get that from the R. So let me just give you the equation. it's a funny looking equation. So what we solve for is 1 over the effective resistance. So 1 over the effective resistance is 1 over R1 plus 1 over R2 plus 1 over R3 and plus 4, 5, 6, 7, 8, etc. Okay, so let's quickly apply it to this problem here. I'm going to do it off to the margin. So what I'm saying is 1 over effective resistance of the circuit is 1/2 plus 1/4 plus 1/8. All right, you can do this on a calculator. I'm going to do a common denominator. So 1 over R effective, the common denominator being 8, is 4/8 plus 2/8 plus 1/8, and that equals 7/8. All right, hopefully remember how to do common denominator. Now that solves for effective 1 over effective resistance. So to get the effective resistance, I got to take the reciprocal of both sides. That's 8/7. I believe if you punch out 8/7 on your calculator, you will get 1.14 ohms. Okay, so that's the odd thing about a parallel circuit, is that the resistances don't add up to the overall resistance. So you got to use that equation, and it directly comes from these two rules for voltage and current. I'll just show you in class how that is. So let me give you a few shortcuts about effective resistance to help life in more complex problems. Okay, if you notice, I have a 2, a 4, and an 8, and my effective resistance is 1.14. If I were to add, you don't have to draw this on here, let's say 1,000 ohms to this, it would have essentially no effect on the overall resistance, because if you recall, these summed up to 7/8. If I add to it 1,000th, that's barely going to change anything. So when I take the reciprocal, there's not going to be much change at all. Okay. However, if I were to add, let's say, a 1 ohm resistor in parallel, okay, to my 7/8, I would add 1 over 1, which would make it 15/8. That would have a significant change, and the reciprocal of 15/8 would be 8/15. So now my resistance is even less. Okay, so if you do this enough, you'll see a pattern emerging, which basically says the effective resistance is always less than the resistance of resistor of smallest value. So in this initial example, our smallest resistance was 2 ohms, so we know the effective resistance must be less than that. And you can show yourself why that must be mathematically based on this equation. Okay, another nice shortcut is if the resistances all have the same value. So let's say I had a 2 ohm by itself. The effective resistance would be 2. Let's say I had a 2 and a 2 in parallel. In other words, I had 2 2s. The effective resistance would be 1 over 2 plus 1 over 2 is 1. Reciprocal of that would be 1. If I had, let's say, 4 2s in parallel, a 2, a 2, a 2, and a 2, it would be 1/2 plus 1/2 plus 1/2 plus 1/2, right? That is 4 halves. Reciprocal of that is 0.5. So we see as we add more and more in parallel, we get less and less resistance. And the effective resistance, when they're all the same, if you look at this, is nothing more than the value of the R, the value of the one given, divided by the number of resistors. Okay, so in this example here, I have 2 resistors of 2, so 2 divided by 2 gives me 1, right? And here I have 4 2s, so if I take 2 divided by 4 of them, I get 1/2. So that's a nice little shortcut to remember. All right, so let's finish up with this with power. Okay, so the power output's pretty straightforward. Voltage times current, 72 watts, then 36 watts, then 1.5 times 12, I believe is 18 watts. And so we see the most powerful one is the one with the most current, the one with the least resistance. That's what we learned when we first did simple circuits. Add them all up, we get 100, 110, 120, 126 watts. And if I do V times I, sure enough, I'll get 126 watts. Okay, so again, it's very similar to what we saw before. When we go across, we have Ohm's law. When we go down, we have the Kirchhoff's rules, or a new resistance equation. Okay, so how does the current change as the number of resistors in parallel increases? Well, I've already alluded to that. More resistors means less resistance. Yeah, say that a few times to let that sink in. More resistors means less resistance. In series, more resistors means more resistance, okay? Therefore, you get more current. So as you keep plugging things into an outlet, if you have a power strip, you keep drawing more and more current as each branch adds up. But the individual currents, sorry, I just massacred that. Okay, but individual currents in each branch must remain the same. So if I've got two objects plugged into an outlet, if I turn one off, it doesn't affect the other one because they're connected in parallel. In other words, they both feel the same voltage, but the different resistances get different currents. Okay, and that's all because of the loop rule and the junction rule. Okay, which has a bigger effect on effective resistance? One insert in the current in a circuit, adding a 1 ohm resistor or a 100 ohm resistor. I already kind of went through that earlier, and essentially it's the 1 ohm resistor has a much bigger effect because the resistance overall must be less than the smallest one. So if I go from 1 being my lowest, now it's going to jump quite a bit. Whereas if I put 100 ohm in there, it barely changes anything. So when you put a large resistance in parallel, it draws very little current and has very little effect. Okay, and that leads us to the last idea here. 4. A voltmeter must be placed in parallel with resistors. We know that already. Since the voltmeter is just a measuring device, is it supposed to affect the current flow in a circuit? And of course, the answer is no. So what does that tell us about the resistance of a voltmeter if it's not supposed to add any current or change the current in a circuit? Well, it must be very, very high. Just the opposite of an ammeter. In fact, it should be an ideal voltmeter has an infinite resistance. So that if I have a simple circuit where the current in here is what it is, if I put a voltmeter across it like I'm supposed to, I don't want to add another branch of current. All right, there's got to be a teeny tiny amount of current here to go for it to register, but we want it to be essentially 0, so we need this resistance to be very, very high. Okay, ammeter, low resistance, voltmeter, high resistance. All right, those two together, basically now we can apply to more complex circuits, which will be our next topic.